Almost all sorting algorithm can be done in two ways: in-place implementation or out-of-place implementation. So always in-place implementation is a bit difficult because using in the case of out-of-place implementation we use an auxiliary array. So in that case things become easier. So when you have to do all the work in the same array, it gets a little difficult. So in the lectures I'm going to always follow the in-place sorting algorithms. So it's up to you to try both implementations. So insertion sort is another very easy sorting algorithm. So in the in-place version, we take the first element first, and we make sure that this array of length 1 is sorted. And an array of length 1 is always sorted. So if we consider the second element, notice that 10 is greater than the last element. So this 2 is sorted. If we consider this part, 4 is not greater than the last element. So we can swap 10 and 2. So let's write it. So even though I'm drawing a new array, you have to understand that this array and that array are same. So we write 2 here, then compare 2 with 10. So this was our first array of length 1. Then we make an array of length 2. Consider the second element, which is 10. So second element 10 is greater than the previous element, so 2 10. Then we consider the third element, so 4 is less than 10, so this should swap with 10. So 4 10. And also notice that 4 is greater than 2, so 4 should stop here. So this part of the array is sorted 2 4 10. Then we consider the fourth element 3, which is less than 10. So we should try to get 3 as left as we can. So since 3 can swap with 10, so we swap it 3 10. Then we try to move 3 further left. So since 3 is less than 4, we can swap them. Then if we try to move 3 any further left, we find that 3 is greater than 2, so we cannot swap them. So we stop here, and this part of the array is sorted. Then we consider the fifth element 12, and it is greater than the last element, so it stays where it is. Then we have 1, so we compare 1 with 12 and swap them. Then we see that we can move 1 even more left. So then we compare 1 with 4 and swap it. Then compare 1 and 3 and swap. So 1 has found its place. So we stop now. So then we consider the next element, which is 5. So 5 can swap with 12. So we swap them. 5, 12. And 5 can also swap with 10. And 5 cannot go any further left because 5 is greater than 4. Then we consider the next element, which is 8. 8 can swap with 12. And 8 can swap with 10 as well. So finally, the whole array is sorted, and so this is how the insertion sort works. And in the insertion sort is special from selection sort or um, bubble sort in the sense that it has a best time or worst time complexity, because the bubble sort always runs for n into n plus 1 by 2 iterations, or almost n square iterations, and so does the selection sort run. But in the insertion sort, uh, if the array was already sorted, so suppose we had 1 2 3 4 5, so since this array is already sorted, bubble sort will still compare these elements and not swap, compare 2 3 and not swap, compare 3 4 and not swap. So bubble sort is always do all the same amount of work, so we'll do the selection sort. But in the insertion sort, what it will do is it will look at the first element and see it's fine, then it will consider the second element. 1 and 2 can swap, then 3 and 2 cannot swap, so 4 and 3 cannot swap, 5 and 4 can swap. So the insertion sort algorithm is done. So the insertion sort does the least amount of job while sorting in an already sorted array, but bubble sort and selection sort always does the same amount of work whether the array is sorted or not. So when the array is sorted, insertion sort gives us a um, some sort of efficiency boost. So let's code this algorithm. We write a function called int insertion sort. Um, so we have to use an index for the next value we are considering. So at first we consider the first element, which is I equals to 0, then until uh, the last element of the array. So uh, then we start comparing the value of the new index, which is ai, with the value on its left, which is j equals to I minus 1. So uh, so at first we are comparing, um, notice that the first value for j will be I minus 1, so ai minus 1 will compare with ai. Ai is the latest value, so if we can swap them, we just swap them. So after the swapping has been done, notice that we should if this condition doesn't hold, so if we cannot move the value any further left, so we should stop the loop, else just break. So this is our implementation for the insertion sort algorithm. So you should write this code and run it and try to understand how this code works, and then you can modify and change this code to make it recursive, or you can use while loop instead of for loop, or you can sort these values from the biggest number to the smallest number, and so on. And and you will probably learn how we can optimize this code. I don't know how we can optimize this code. This looks like the most optimized code for insertion sort. So that's it.